Okay, hello and welcome to the first video review for our first test of the new school year, the Week 3 CCA. As I said in class on Monday, one of the main problems that I saw on the quiz was people not being able to obtain slope easily and efficiently, because in a lot of you guys you were overthinking it. So I'm just going to go over this real quick again. When we have slope, let me make this a little straighter. In math we were taught that we have y over x, and if we have a point, 2 points, one being x1, y1, and the other being x2, y2, our simple algebra tells us that the slope of this line is equal to y2 minus y1 and x2 minus x1. And we said what happens in physics that sometimes kind of throws us is that instead of on the y-axis it being labeled y, there might be an x, because in physics displacement is a lot of times given the symbol x if the motion is left to right, in other words horizontal in the x-plane, then we put x on the y-axis because that is our displacement. If the motion is up and down, then we say that is in the y-axis, and you might even see y on the y-axis. So it's very important to keep that little bit of a difference in mind when we're in physics. And also, I know you learned this in math, but it's very important in physics, is that if we have a straight diagonal line, we have to remember that the slope is the same no matter what 2 points you take on that line. You can extend that line to infinity, the slope is still going to be the same. So in the bottom graph, when we take the slope as we did in the in one of the versions of the quiz, they asked for the slope at the point 1.4, where time is equal to 1.4. And some people took their point as their x point having to be their x2 point having to equal 1.4, and then finding what y was by trying to eyeball it. And because they really couldn't do that very well, they were getting the wrong answer. What's important to realize is the slope at 1.4 is the same as the slope at 5. So at 5 we can see that y is exactly 10. So it would be much better to get that slope by saying that we have 2 points, 5, 10, and 0, 0. So that way, when we took y2 minus y1, it would be 10 minus 5. And of course, those units are meters per second. And excuse me, not 10 minus 5. Take that back. 10 minus 0. And 5 minus 0. And what's nice is that in physics, especially in Newtonian physics, time is always going to be positive. We have not found a way to go back in time yet, so it will always be positive. The top, though, could be negative, especially if the slope is down, like it is in this section right here. In this section, our slope, we can tell by looking at it that it is a negative slope. However, if you follow your slope rules, you're going to find out that it's negative anyway. So for instance, again, if we are taking that the slope is equal to y2 minus y1 over t2, well, x, let's use our physics variables. If we're going to say that it is v2 minus v1 over t2 minus t1, the very final velocity is 25. The initial velocity was 40. And the time was 25 minus 15. Therefore, we will automatically find a negative number up here. This will be a negative 15 divided by 10, which will give us a negative 1.5 meters per second squared for the acceleration in that area. So, just a few things to keep in mind about slope. Of course, then we also needed to remember whether or not to use the slope or the area. And again, we had the little DIVA acronym that I gave you, DT, VT, and AT. And the way it went is that if I have a displacement time graph and I want velocity, I should always take the slope. If I want the velocity, or I have the velocity time graph and I want acceleration, again, I take the slope. On the other hand, if I have acceleration time graph and I want velocity, I'm going to take area. And likewise, if I have a velocity time graph and I want displacement, I'm going to take the area. Okay, so now let's look at some actual problems here. Here is a side-by-side view of what you took in your notes. If you don't have this, if you were absent a day or for some reason couldn't get it down, you might want to put this down in your journal when you get a chance. And it's interesting to look at this where we can see side by side at rest, constant velocity, and constant acceleration. So looking at our displacement time graph, remember our first rule when trying to analyze any graphs is what is on the y-axis. So on this y-axis we have displacement. The displacement is labeled as x. In a displacement time graph, if the object is at rest, we've got a straight horizontal line. Notice the next is at constant velocity, it slopes up, and then at constant acceleration, it curves up. And the next one, for velocity time graph, if it's at rest, then it obviously is going to be at 0. Here's our velocity time graph. Okay, if it's constant velocity, it'll still be a straight horizontal line, but it'll be something other than 0. And if it is on a constant acceleration, it'll be a straight horizontal line. And last but not least is the acceleration. And remember, we said the one thing we know about acceleration graphs in kinematics, because the acceleration is always constant acceleration, it'll always have a very blocky form type of graph, because we will never have changing acceleration in kinematics, because that is the definition of kinematics, is when the acceleration is constant. Not necessarily 0, but it is constant. Okay, so the first thing I want you to look at are these two graphs up here, and you need to be able to compare and contrast these two graphs. These two graphs come right off of an AP workbook and test questions, and or one similar to it. And what I want you to do is, first of all, your first rule of thumb is to look at these two graphs and see what is on the y-axis. Well, when we look at the y-axis, we see that we're comparing velocity. We're comparing velocity to time here. So in the first graph, we start out with what is a constant velocity at 2 meters per second, and it goes for 1 second. So this is 2 meters per second right here. It goes for 1 second and then turns totally around going the opposite way and goes a negative 2 meters per second for 1 second. How do I know that it turned around and went the opposite way? Because it crossed the zero line. Remember, in velocity, if I have negative velocity, it means that it turned and went back the other way. So essentially, if I was looking at this object, let's call this graph A. If I was looking at this object, I would see it going for 2 meters per second for 1 second, and then turning around and coming back exactly to the place it started, because it went for 1 second again at 2 meters per second, but only in the opposite direction. So then it starts out again and goes another 2 meters per second in the same direction that it did before. So this is the starting direction. If the starting direction was north, it went 2 meters per second. It went for 1 second, it went 2 meters per second north, and then for 1 second, it went 2 meters per second south. Turns around and goes 2 meters per second north again, and then turns right back around and goes 2 meters per second south for another negative 2 meters per second for 1 second. So therefore, if we were looking at this object, it would be right back to where it started from, because this was the north, this was the south, no, this was the north, this was the south. So the conclusion here is that this object was just going up and down, back and forth. On the other hand, this object, and we're going to call this graph B, this object started out at 0. It was increasing its velocity all the time, so therefore it was increasing in acceleration from 0 time to 4. So when we want to get the